Hi, this is Mr. Singh here. Today we're going to be looking at sound waves, which is part of the AQA physics syllabus. Before we start that, have I got these, pause the video here and have I got these 5 retrieval questions, please? Okay, let's have a look. So number 1, name 2 types of waves. That will be longitudinal wave and transverse wave. Number 2, what's the difference between these two waves? Longitudinal wave is where the flow of energy is parallel to the movement of the waves, and transverse is where the flow of energy is perpendicular to the movement of the waves. Number 3, why can sound not travel in space? Space is a vacuum, there's no air, so sound cannot travel in a vacuum. Number 4, how do we communicate in space then? We use radio waves, which are part of the electromagnetic spectrum. And number 5, which is faster, sound or light? Sound travelled at 330 meters per second, whereas light travels at 300 million meters per second. So you can see light is faster. If we move on, 3 objectives there. You can have a look at this. The key words: vibration, eardrums, reflect, frequency, and hertz. Is something you need to pause and think about and try and jot down something here. How is sound transferred and how is sound detected? Okay, hopefully you'll have a better understanding at the end of this lesson. So you can see sound travels as a longitudinal wave just at the top there, and you can see areas of low pressure, which are rarefactions, an area of high pressure, which are called compressions, and they are supposed to be air particles. Now, sound can pass through an instrument called an oscilloscope, and the oscilloscope will convert that into a transverse wave, which you can see at the bottom here. You can see the height of the wave is called an amplitude. The wavelength is the distance between two successive peaks. You can see rarefaction, what happens to how does it look in a transverse wave, and you can see compression. You can see what that looks like in a transverse wave. Sound, as we have said, is a longitudinal wave caused by vibration objects. Vibrations are passed via compressions and rarefactions. Sound requires particles, therefore doesn't travel through a vacuum. Sound travels faster in solids than liquids. See if you can figure out why the speed of sound is faster in a solid than a liquid, and sound travels faster in liquid than gases. What you should have remembered here is how the particles are arranged in a solid, liquid, and a gas. And because point number 2 says caused by vibrating objects, in a solid, the particles are very closely packed together. So when one particle vibrates, pretty quickly, soon after that will bump into the next one, and the next one, and the next one, and they will all start to vibrate, and so sound is travelling faster. Whereas in a liquid, the particles are spread out, and in a gas, they're even further spread out. Sound cannot refract. So, what is the equation for calculating wave speed? Now, this equation you definitely need to know. Wave speed equals frequency, which is the number of waves passing a point per second, times a wavelength, which is the distance between two successive peaks. Frequency is measured in hertz, and wavelength is measured in meters. So, here we go. A sound wave with a wavelength of 0.7 meters moves from air to water. The speed of the wave changes from 330 meters per second to 1500 meters per second. What is the new wavelength of the sound wave? The frequency of the wave remains constant. So pause the video here. You will need to rearrange the equation. That's the equation. So it's asking for the new wavelength. Frequency remains constant. Okay, let's see how you got on. So frequency equals wave speed divided by the wavelength. 330 divided by 0.7, 471 hertz. And in water, 3.4 meters. So you can see the new wavelength. We can hear frequencies between 20 hertz and 20,000 hertz. Don't forget, hertz is a measure of frequency. When a person talks, they cause the surrounding air to vibrate. This creates compressions and rarefactions. But then what happens inside the ear? So this is a picture of the ear. You can see that. Sound travels along the ear canal. Ear drums begin to vibrate and pass its vibration via the small bones called ossicles. And the vibrations reach the cochlea, which turns the vibrations into electrical signals which go to the brain. Make a flowchart to show how we hear sounds. Okay, once you've done that, let's move on. Here's some past questions for you. Figure 1 shows a longitudinal wave being produced by a stretching spring. Which of the letters on Figure 1 shows the centre of a rarefaction? And B, which two letters in Figure 1 have a distance of one wavelength between them? Let's see how you got on. So, K for 1 mark, and L and M for the 2nd mark. C, describe how the end of the stretched springs should be moved in order to produce a transverse wave for 1 mark. Okay, so there you go. Allow up and down also. Figure 2 shows how 2 students use the sound reflected off a building, an echo, to measure the speed of sound. Here's some questions for you to do. Okay, let's see how you got on. That's 1 mark. Another question, calculate the mean value of the time for 5 echoes. Ignore the anomalous result. The answer is 3. 2 more questions for you. Pause the video. Have a go at these. Okay, let's again see how you got on. 750 meters, 1 mark, and there's your 2 marks. Okay, let's move on. Final question, 2 marks. Have a go at this. Suggest 2 changes to the method used by the student that would improve the accuracy. Pause the video here. Okay, if we look at this, there you go. Any 2 from. 3 answers there, 2 marks. And that question was worth 10 marks. And that concludes our lesson.